those of you who are watching, I forgot to record the first 8 minutes. All I said during those first 8 minutes are, this is a function I've posted. Be sure to look at it. The comments in the file indicate how the function works. You don't need to be concerned with the inner workings of it, but just having understanding what the input and the output mean. And that is described in the comments in this function. Okay. Now, so just to recap, methods for approximating derivatives. Okay, I need to make sure my notation is consistent with the book. Okay. All right, minus j, okay. I equals minus j to k of ci f of xi. All right, now we want a derivative at x naught. Now the reason I have these weird indices going from minus j to k is to indicate that points with negative indices would be to the left of x naught, and points with positive indices would be to the right of x naught. So for instance, I could have x sub minus 1 equal x naught minus h, and then x sub 1 would be x naught plus h. So they all have this form. It's a linear combination of values of f at the point itself and nearby points on either side, left or right. So the whole problem boils down to, how do we get these coefficients? Okay, so how to get the coefficients Ci, two approaches that yield the same result, but okay, the first one was Taylor expansion of f of xi around x naught. So each one of these is Taylor expanded around, so x naught is the center of that Taylor expansion. So what happens is you'll get a bunch of terms that have f of x naught, f prime of x naught, f double prime of x naught, and so on. So then group terms by what I just mentioned, f double prime, x naught, etc., and set coefficients of f prime of x naught to 1, because you want this to reduce to f prime of x naught plus some error, and of all the other derivatives of f, including the zeroth derivative, which is f of x naught itself, to 0, to wipe those out as much as you can. I mean, you only have so many coefficients. That means you can only impose so many constraints on them. So you do the best you can with that. To get a system of linear equations of this form, A times C is equal to B. So C, I'll just detail out what these are. So C is equal to a vector containing all the coefficients. So that would be starting from C minus J, C minus J plus 1, etc., all the way down to CK. So from the smallest index to the largest. So those are all the unknowns in our system. And then the vector B is very simple to describe. 0 in the first position, 1 in the second position, and then zeros everywhere else. Okay. And then the matrix A. Okay, I'm using the letters I, J, and K already, so I need to use different letters. So if I describe the entry in row M, column N, so usual notation for matrix entries, it's going to be all right. It's going to be a difference of x values. Okay, so xm minus x naught. I have to fix this a little bit. I'm going to fill these in a bit at a time. To the no, it's x n minus x naught. Don't write anything down yet. This is an expression in progress. To the m minus first power, and then the index down here needs to be okay, so when n is equal to 1, okay, I need to be minus j, so I need n minus 1 minus j. Okay, so these are the formulas for the entries of that matrix for, I'll use typical MATLAB indexing. Okay, because the total number of points, we have points from 1 to k, and then minus 1 to minus j, and then 0 as well. So it's actually the total number of points is k plus j plus 1. So if you can set up this system of linear equations, so this and I wrote it out this way because you could code this in MATLAB. Like you'd have a vector of x values already, all these x values, and you can write a for loop that would populate this matrix with these powers of these matrix entries. Now, if the points are equal spaced with spacing h, then what would go in here is a multiple of h. So it becomes a lot simpler in that case. And then you can use, and then you can solve the system as normally do in MATLAB. So you can say, whoops, TTs. C equals A backslash, whoops, B. Okay. Okay, so that's how we solve a system of equations in MATLAB. Matrix backslash right-hand side vector gives a solution. That would also be a column vector. Okay. Something's wrong with my LaTeX here. I can't exactly tell what it is. Okay. I'll deal with that later. All right, so this is the Taylor expansion approach. Now, as far as the error formula, comes from first terms in Taylor expansion that don't cancel. So the lowest order terms, because you have a bunch of things cancel. I mean, you'll have f prime of x naught fall out of all this, and then the next term after that describes your error. Okay. Okay. Now the other approach, which actually is a whole lot easier to describe, is this. I can set the coefficient ci equal to Lagrange polynomial derivative at x naught. So in other words, you form the Lagrange polynomials with all your x values. And then you take the derivatives of those Lagrange polynomials, and you plug in x naught. Okay. And that's it. That's the whole method. The error term comes from the derivative of the Lagrange interpolation error at x naught. So in other words, the error to derivative is the derivative of the error. But this formula is actually given in the text. Okay. It's something you work with in one of the problems. Okay. Now, things in case of equal spacing, where xi is equal to x naught plus ih, for I equal to minus j all the way up to k, then the way these approaches simplify, okay. All right. So in the first approach, AMN is equal to, okay. So that'll be, okay, n minus 1 minus j times h raised to the m minus 1 power. Just because I'm plugging in this formula into here with the appropriate index, and all we get is just a multiple of h raised to whatever power. Okay. Okay. Let's see. This is for, again, m and n equal to total number 1 up to the total number of points that you have. And in the case of Lagrange interpolation, can interpolate at the integers xi equal to I. Okay. And then take derivatives at 0, and then divide the coefficients by h. So don't forget to do that. Okay. And certainly the error formulas would simplify quite a bit as well, because the error would be expressed in terms of h. Okay. And I can also say that the order of accuracy is, okay, h to the k plus j. So as an example, suppose I have a center difference. I use 1 point to the left of x naught, 1 point to the right of x naught. So j and k are both equal to 1. So the order of accuracy is h squared. Sure enough, that is the order of accuracy of the center difference. You would have a 3 by 3 matrix. And your rows would be populated with, so if j is equal to 1, I'd have, okay, so, all right, so I'd have minus h, and then 0, and then h, raised to a different power in each row, to the 0th power in the first row, and then the first power in the second power. So that's what the matrix would look like in that case. Okay, so these are methods in a way that is conducive to coding in MATLAB. for coming up with numerical differentiation coefficients of the coefficients in these schemes. And I should say here at the top, okay, that's an approximation plus some error with not so many R's. Okay. All right. Now, and the thing is, it's finicky most of my. I focus more on this approach of Lagrange interpolation, because that's actually the same approach that I'm going to use in a little bit to describe methods for numerical integration. And really, Lagrange is the way to go for that one, as opposed to Taylor expansion doesn't really help so much. Okay. Now, a few words about sensitivity. What is the... I'm going to move this to a new page. What is the condition number of numerical differentiation? All right, so a problem computing f prime of x naught. Now, can anyone tell me this is back from chapter 2. How is the condition number defined? Yeah, forward error. It's a ratio of forward error, backward error. Okay. Now, how are we going to get that in this case? Well, forward error comes from error formulas derived using Taylor or Lagrange. So the error formulas I was showing last time would be the forward error. As an example, we have f prime of x naught is equal to like a forward difference, f of x naught plus h minus f of x naught divided by h, and then the error is equal to minus h over 2 f double prime at some unknown point xc. So this right here, the last term, minus h over 2 f double prime, that's the forward error. So if we, so what about the backward error? What could that possibly be? And for that, we note the following: that backward error analysis is based on the assumption that the computed solution, and using more general notation from back in chapter 2, hat f of x is the exact solution of a nearby problem. So that'd be f at hat x. Now that's definitely true in this case. In numerical differentiation, the approximate derivative, so the approximation of f of x naught is the, f prime of x naught is the exact value of Pn prime of x naught. Dang it. Where Pn x is the interpolating polynomial of degree n, which is equal to j plus k in this case. Okay, so what that means is makes it very easy for us to get backward error in this problem. The backward error is the error in polynomial interpolation. Okay. because what's happening is, if you think of f of x as our input, the function we're trying to take a derivative of, well, backward error is x, the exact input, minus the approximate input. The approximate input is the interpolating polynomial. So the difference between the two is a backward error. So, continuing with this example, so the forward difference. For forward difference, we have a linear polynomial, p1 of x, interpolates f of x at the 2 points, x0 and x0 plus h. So the error is going to be f of x minus p1 of x. So now I'm using the interpolating error formula. So that's second derivative over 2 times x minus x0 and then x minus x0 plus h. Now, it can be shown, I won't go through all the mechanics here, but whenever you have these 2 points of spacing h, and you take the maximum of this, the maximum turns out to be at the midpoint, and it always turns out to be the spacing divided by 4. So this is equal to minus f double prime at an unknown point over 8. Times h squared. Okay. So that's our backward error, and this is our forward error. So what's the condition number? If this is your forward error, this is your backward error. You simplify as much as you can. Yeah, it's 4 over h. Now, that's actually pretty bad, because h is supposed to be small. So this problem is ill-conditioned for small h. And I may have shown this at one point, if I use the forward difference, for example, on a function where I know what the result's supposed to be, and I try smaller and smaller values of h, then you find that the error is going to 0. But once h gets really, really small, like closer to the machine precision or unit round-off, the error increases. And the reason for that is this error formula right here does not take round-off error into account. What happens is the round-off error in this gets pretty substantial when h gets small. So this is why you have to be very careful. You do want a small h for accuracy, but not too small. And in fact, the higher order methods, like for higher order derivatives, or something like a center difference where the error is proportional to h squared, you get away with even less. You have to be even more careful about choosing h too small. Because at some point that cancellation error becomes too great. So this is one unfortunate thing about numerical differentiation. It's just not a good problem. So we do have effective methods for it, but you have to be careful in using them because of this ill conditioning. Okay. Numerical integration, on the other hand, since integration is the reverse of differentiation, that would flip the condition number. So actually, So the last part of my integration discussion, I'll fill in right now, just 2 words. It's well conditioned. And yeah, generally when you have a problem computing something, and then you look at the inverse problem, the 2 problems will have condition numbers that are reciprocals of one another, because if you put the 2 together, your input into one, and then the output of that goes to the input of the other, you end up back where you started. And the condition number of that should always be 1. Okay, but how do we go about, so for a numerical integration, so the problem in this case is approximate the definite integral of some given function over some interval AB. So those are your inputs. F is, so for given F, A, and B. Now, hopefully you'll be given a formula for f of x so that you could evaluate it at any point, but that may not necessarily be the case. You may have to fit f of x with some function like a polynomial to really be able to work with it. But before I talk about methods for approximating this integral, I want to highlight why we need them, because you learn how to integrate in Cal 2, and also there is software that can integrate, that implements those integration techniques, plus other ones that are too advanced for an ordinary Cal 2 class. Okay, so why do we need numerical integration? First, for a similar reason as I pointed out in numerical differentiation, so we have much more efficient than software that implements symbolic integration, which is the kind of integration you do in Cal 2. Because all you're doing, just like in numerical differentiation, we're evaluating a function f at a few points between a and b, or hopefully not too many, and then we're combining those in some way to get the approximate integral. And the goal is to minimize the number of points, and we'll learn different ways of doing that. So that really plays to computer strengths, whereas, again, symbolic integration, you're dealing with expression trees that describe a structure of f and how to work with those. And integration rules are much harder to implement than differentiation rules, because you're trying to look for certain patterns and figure out what to do. And I've seen software like Maple churn on it for a while and then just give up. So that's a problem. Numerical integration methods won't do that. They'll give you an answer. Okay, not always the right answer, but your odds are better, or they're more in your favor. Now, some integrals can't be handled symbolically. So here's a couple of importance. Whoops. What happened here? Oh, I misspelled begin. Okay. Arc length of a curve. This is something you learned about in Cal 3. Of a curve, y equals f of x. And what we have for that is length is equal to the integral from a to b of square root of 1 plus f prime of x squared. Dx. And even if a function f itself is pretty easy to work with, chances are this expression here, the square root of 1 plus f prime squared, is something that it's not likely that you'll be able to integrate that using Cal 2 techniques. And it's funny, whenever I teach Cal 3, where this comes up, and I look at the problems that textbooks give, and they come these really weird curves where it's all contrived for you to be able to work out this integral. And it's like, yeah, like that ever happens in nature. So it's just kind of silly. So numerical techniques are best for that. Also, a Gaussian function. So an integral of a function of this form. Okay. Can anyone tell me where else in mathematics does this kind of function pop up? Where might you have you seen this in another class? There's actually more than one answer. What? Really? Oh. Okay. Well, it does play part in partial differential equations, but I know you haven't taken that class yet. Depending on the examples given, it might pop up in Laplace transforms in differential equations. Anyone else?
I think I saw this in number theory.
Interesting. I wouldn't expect that, but.
It may not have been that class. It was just some class of Dr. Theory. I'm not remembering if it was number theory or modern. One class of Dr. Theory.
Okay. What's another? Yes, definitely probability. That's the answer I was looking for. But yeah, it comes up in several fields of math. I figured probability is one you're most likely to have seen it in. Okay. Yeah, this function cannot be integrated using any analytical integration technique. It's been proven that there's no answer in terms of elementary functions. So don't even bother. Yeah, so it has to be done numerically. Okay. So, similar to differentiation, the form of the approximation is, so the integral a to b f x dx is equal to a sum. Again, I want to check my notation here. Okay. Okay. I equals 1 to n of xi wi. Now, this approximation is called, okay, it's equal to that. That's the approximation plus error. Okay. So this approximation is called a Quadrature Rule. And what determines a Quadrature Rule are these quantities. The xi are called the nodes, and the wi are called the weights. All right, so once you have the nodes and the weights, that defines your Quadrature Rule. So then you can just substitute the nodes into your integrand, your f of x, multiply those values by the weights and add them up, and bam, you have your approximation. So the challenge here is, how do we choose the nodes and weights to obtain as much accuracy as possible and as efficiently as possible? So want the number of nodes and to be as small as possible while still obtaining sufficient accuracy. Sufficient accuracy. Okay. Now, so in fact, that's how the efficiency of a Quadrature Rule is judged, by n. How many function evaluations are going to be performed? Because sometimes a function n might be expensive to evaluate. Not if it's something simple like x squared, but it could be some monstrosity. So it could be a real bottleneck computationally. Okay. So So what I'm going to do is focus on a particular type of quadrature rule, and really that'll be for the whole chapter, that leads to the most widely used methods. Okay. So to get some guidance on how to choose the nodes and weights. Okay. So first question to ask is, which functions are easy to integrate? And the second question is, once we have that in mind, how can we approximately integrate a general f of x using these easy functions? Okay, so the idea is presumably that'll put us in the right path to getting nodes and weights. So what functions are the easiest to integrate? What type of function? Yeah, polynomial. So a lot from polynomial interpolation, what we saw was a differentiation, and it's even more true in integration. All the time we spent on polynomial interpolation is helping us here with these problems. Okay, so that leads to interpolatory quadrature. So the idea is, given the nodes... Oh, shut up. Okay. All right, fine. All right, that'll cut 1/3 of the noise. So I'm not going to talk much yet about how we choose the nodes, except that it should be in the interval AB that we're integrating over. That would make sense. So given these nodes, what we do is, hello, what happened? Okay. You approximate the integral of f of x with the exact integral of a polynomial Pn minus 1 of x that interpolates f of x at the nodes x1, x2, all the way up to xn. So we have n nodes. So as you know from the previous chapter, polynomial that interpolates at n nodes will have degree 1 less. So that's why I have n minus 1 here. Okay. So the idea is the approximation of the integral will be the integral of an approximation. In this case, a polynomial approximation. Okay. So we take a closer look at that. We write Pn, n minus 1 in Lagrange form. Okay, so what we do is the integral of f, okay, is approximated by, okay, the integral of this interpolating polynomial, but that equals, so if I write this in Lagrange form, so this will be a sum of n terms, and because we're interpolating f at these points, these are the coefficients of Lagrange polynomials. That, as you know from Lagrange interpolation, the coefficients are just the y values. And then we multiply that by the appropriate Lagrange polynomial. Okay. But with the integral being linear, we can factor out, we can pull out sums, and we can pull out constants. So I'll have a sum of fxi, and then what's left is okay. All right, so now the approximation has this form. So it's the sum of n terms. Oh, wait a minute. Sorry, my notation is kind of like from a previous chapter, but I need to adjust 1 to n instead of 0 to n minus 1. Okay. All right. Now, if I compare this to the form of a quadrature rule that I put earlier, what do we have? Sum from I equals 1 to n, f of xi times wi. Well, now we go back down here. Sum from I equals 1 to n, f of xi times this mess. But that's a constant. That's the weight. So therefore, wi is the integral from a to b of the ith Lagrange polynomial of degree n minus 1. So in other words, with interpolatory quadrature, once the nodes are chosen, we have the weights. And they come from the integrals of Lagrange polynomial. Okay. Now, I want to draw a parallel between what I've just shown you here and how it works for numerical differentiation. So we call numerical differentiation the coefficients in the approximation are given by Ci is equal to a Lagrange polynomial of some degree. What is going on here? Okay, n. Okay. Prime at x naught. Okay, so in numerical differentiation, we want f prime of x naught. So what do? We do that to Lagrange polynomials. Take a derivative, plug in x naught. Here, we want the integral of f from a to b. So we integrate to Lagrange.
It might be in the video.
We'll find out. The integral of Lagrange polynomial from a to b. So in other words, whatever problem we're trying to solve, whatever derivative, whatever integral, we carry that out on the Lagrange polynomials. And that gives us the coefficients that we multiply the f values by in both cases. Okay. So that's true in any case we're trying to approximate something done to f by the exact problem solved on the Lagrange interpolant. Okay. Okay, just want to see what else I have here. Okay. So there's one important term I need to define. So this will come up quite often. The degree of an interpolatory quadrature rule is the highest degree of polynomial that is guaranteed to be integrated exactly. Now, for an n-node rule, the degree is at least n minus 1. Because suppose f is a polynomial of degree n minus 1 or less, then this f of x would be equal to this polynomial here. And therefore, the exact integral of this is what the quadrature rule gives. That would be equal to the integral of f. So we always have that. What we will see is that in some cases, like due to some nice things working in our favor, like symmetry, etc., it's actually possible to get a higher degree of accuracy than n minus 1. So, for example, one of the rules we'll see, it's called Simpsons Rule. It's a 3-node rule, so you'd think the degree of accuracy would be 2, but it's actually 3. All right, but it'll never be less than this. Degree of a polynomial. So degree. Okay, so the degree of accuracy of a quadrature rule is the highest degree of polynomial that will be done exactly. So we say that Simpsons rule has degree of accuracy, or simply degree, of 3, because it'll integrate all constants, linear functions, quadratics, and cubics exactly. But if you give it a 4th degree polynomial, in general, it will not be exact. Okay. Actually, what we will see towards the end of a chapter is that for an n-node rule, the highest degree we can possibly get is 2n minus 1. That's called Gauss quadrature, but we'll see that much later. It's one of the more difficult rules to understand and actually work with, but because of its high degree of accuracy, it's very popular. Another important point to make is the weights of any quadrature rule should be positive. And this is not necessarily assured. So the ones that we'll deal with, they will have positive weights. But sometimes you might think, oh, if I'm using more points, more nodes, I should get more accuracy. And it turns out that's not always true. It depends on how you choose them. You might end up getting some negative weights in there, and then a quadrature rule of negative weights is useless. It's numerically unstable. So it's important to steer clear of those. Oh, now I hear a train down at the coast. Noises everywhere. Okay. Now. Okay. And I won't say any more about sensitivity. It's well conditioned, since as a kind of a consequence of differentiation being ill conditioned. Okay. That is actually all the new material I needed to cover today. So, does anyone up here or down there have homework questions? What a quiet bunch you are. Or I should say 2 bunches. The only people who aren't quiet are the ones outside here. Well, yeah, up in Hattiesburg, we don't have very many people here. So, well, you asked me your questions already. Okay. Okay. Well, if anyone wants to ask me questions individually, they can stick around, whether up here or down there. So I won't make everybody else stay. So.